Okay, so now we'll see what is a global state recording and an algorithm to do it. So first of all, what is the global state of a distributed system? It's a collection of all the local states of all the processes and the states of all the communication channels. So what is the local state of a process? So the local state of a process is basically a collection of events that happened at the process. The events could be the internal events, or the sending of a message, or the receiving of a message. So all of these things put together will constitute the local state of a process. Similarly, the state of a channel is a collection of all the messages that have been sent by some sending process on to the channel and not yet delivered to the receiver. So putting together all the local states of all the processes and the states of all the communication channels constitute the global state. Now we are interested in classifying whether the global state is called what is called a consistent global state, and if so, is it also strongly consistent, or if it's not consistent, it's what is an inconsistent global state. Now, a consistent global state has to satisfy these two conditions. Now, if a process PI has sent a message M, then that message and that process PI sent that message M to process PJ, then in the local state of if the sending of the message is recorded in the local state of process PI, then the receiving of the message should be recorded in the local state of process PJ, or the kind of the transit of the message should be recorded in the channel from I to J. And that's what this condition states. If the sending of message M from I to J is recorded in the local state of process I, then it implies that the message should have been recorded either in the channel from I to J that it is in transit, or it is recorded as the received message in the state of process J. Okay, so either one of this. And if the sending of a message is not recorded, if I has sent something to J, message M, but if the sending of the message M is not recorded at process I, then it should not be recorded in the state of the channel from I to J, as well as and in the state and should not be recorded as received in process J. So if the local state of a process I did not record the sending of a message, then that message should not be recorded as received in the receiver process J, or as being in transit in the channel. Okay, so if these two conditions are satisfied, then the global state is called a consistent global state, of course across all the processes and across all the channels. Now, what is called a strongly consistent global state is basically if there are no messages in transit. So if the state of all the communication channels is empty, then we can say that global state, if it's a consistent global state, it's also a strongly consistent global state, which means essentially all messages that were recorded as being sent in the sending process should have been also recorded as being received in the receiving process, essentially implying that there are no messages in transit. Now, what is an inconsistent global state? So if a global state records even one message that has been sent after the recording of the local state of the process. So essentially, the message has been it should be reworded. Is the one that records receiving of the message and the sending of the message is not recorded. This one that records receiving of the of a message in the receiving process, or in the or as the transit message channel, but the sending of the message is not recorded. So that's the correction. So an inconsistent global state is the one that records the receiving of a message in the receiving process or as a transit message in the channel, but the sending of the message is not recorded, which means you basically have a kind of orphan message that appears to have been received or being in the channel, but you have not recorded the sending of the message. So such a global state, so even if one such message exists when you capture the global state, then it's called an inconsistent global state. Okay, so we have an example here. So if you look at this, we don't have any messages in transit because we have only one message essentially, and the sending is recorded here and the receiving is recorded here, and this is the snapshot in which you're at the time basically at which you're collecting these global state across all these processes, and all the messages sent have been also recorded as received. Okay, whereas here if you see the two messages, of course, if you start from this point and you have this sent and received, but this message has been recorded as sent at this process, but it's not yet recorded as at this process as being received because your snapshot is collected at this time. Okay, so this message, as you see, it crosses this kind of line. So we call this actually as a cut. A cut is basically a snapshot of the system at some point of time. So we kind of collect the local states of these processes at this time instance, need not be at one single time across the different processes at different times, but put together it constitutes a cut. So you can see here this message kind of crosses the cut, but it is being recorded as being sent, so that's fine. Okay, so it's a consistent cut, but it's not a strongly consistent cut because there's a transit message. Now if you look at this kind of cut or a global state, so a cut is basically a representation of a global state, a snapshot of the system across all the processes and the channel. So you see here this message is sent after the local state is recorded at this process, but this message is being recorded as being received before you record the local state of this process P3. So it's a kind of orphan message because this message has not been recorded as being sent in the global state. So we call that global state as an inconsistent global state or inconsistent cut. So a cut is a kind of a graphical representation of the global state of a process, of the system, collecting all the local states of the processes. So we can say a cut is collection of what is called cut events. So a cut event is said to happen at the particular process Pi. So this is a cut event for this global cut, this cut. This is the cut event here, this is a cut event here, and this is a cut event here. So we essentially can associate a timestamp, a vector clock, with each of those cut events. So let me walk over to an example. So for the same example that we saw earlier, this is the vector clock of this event, essentially sending this message, and this is 110 receiving this. Okay, and there's be no event in this process, so this clock is 000. Now if you look at this the cut events at these processes, when this event happens, it's not internal or sending or receiving event, is a cut event, so we don't increment the clock value. But when you kind of capture the snapshot, this is the latest time vector clock. So this is the vector clock of this cut event at process P1, this is the vector clock of this cut event at process P2, and this is vector clock at process P3. So we can now associate what is called the vector timestamp of the entire cut. The vector timestamp of the entire cut is essentially the maximum of the individual entries. So we compare this 0 with this 1 with this 1, the maximum is a 1, and we compare this 0 with this 1 and this 0, it is a 1, and 0, 0, and 0, that's maximum is 0. So this is what is called the vector timestamp of this cut. Okay. Similarly for this, so you are sending a message, so it's incremented from 110 to 120 from process P2, and you're receiving this, so this is 1 2, and then this is incremented from 0 to 1. Now, when this cut event cut was collected, this is the time, so same 1 0 0 because no other event happened, and this is 1 2 0 because this is the latest time, and this is still 0 0 0 because no event happened until this point. So if you again take the component wise maximum, is going to be a maximum of 0 1 and 1, that is 1, the maximum of 0 2 and 0, that is 2, and the maximum of 0 0 and 0, that is 0. So this is the time of this vector timestamp of this cut. Now we can also find out whether the particular cut with this given timestamp is a consistent cut or not by looking at from where these individual entries came from. So this 1 is essentially here in both this processes P1 and P2, but the first entry you can also see in process P1, that is a 1. The second entry here is 2. You can see that only P2 has a 2 here, and the third entry is 0. All the three processes have a 0. So if the individual entries are the maximum values in the corresponding processes clock also, then we can say such a cut is consistent cut. For example, this 2 is only this 2 is a it corresponds to P2's kind of individual entry, right? Sending process P2. So now of course we cannot use vector clock to distinguish between a consistent and strongly consistent cut. Just for a consistent cut, including whether it is a strongly consistent cut, it should satisfy the property, and that's what I show here. If the values came from the individual processes component clock values, then we can say that cut is a consistent cut. Now look at this. So this is the timestamp 200. You sent another message and then no other event, and then this message has been received. So the last entry is incremented from 1 to 2, and then you take a component wise maximum, so 2, and then this is already 2, and then a 2. So when you record the time for all these cut events, this is 100, the latest time so far, and this is 120, the latest time so far, and this is 222, the latest time so far. And if you try to take the component wise maximum, it is maximum of 2, 1 and 2, it is a 2, and then 0, 2 and 2, it is a 2, 0, 0, 2 is a 2. So this is the vector timestamp of this cut. Now if you can see, this 2 should have come from process 1, and that is there 2, and this 2 should be there in process 2, it's 2, but this 2 should have come from process sorry, I made a mistake. This 2, these are the cut events, right? These are the time stamps for the cut events. 100, 120, 222. So I looked at this. So this the first two should have come from process 1, whereas process 1, the time stamp for this is a cut event, right? This red line. So the timestamp at process 1 is still 1, whereas in the cut we record it as 2. So it did not come from that particular process. Okay, for the other two, this 2 from process 2 and this 2 from process 3, that's fine. Whereas this 2 should have come from process 1, but process 1, the cut event is, the timestamp is 1. Okay, so that's why it is not a consistent cut. Alright, as here you see here, this 1 should have been from process 1, it is 1 here, this timestamp of this cut event, this 2 for this time cut event, and 0 process 3 cut event is 0. Whereas this 2, if it is a consistent cut, should have come from process 1, whereas process 1 the cut event timestamp is 1 here. Okay. Alright, so we are going to look at an algorithm now to record the global state. That's the Chandy-Laporte algorithm. So essentially what happens here is we have an initiator process that initiates this recording. So as you know, the global state is a collection of all the local states of the processes. So we have this processes collecting the local states and then sending their local states to this initiating process, including the channel states. So The initiating process records its local state as a collection of all the messages that it has sent and received so far, and sets out a marker. Now it has not sent any message, so it records the message or the local states and sends out a marker on a communication channel. A marker is a small control message, and it sends out the marker on all the channels connected to that process. And when a process receives that marker, if it has not recorded its local state already, it records again all the messages that it has received so far, and then records the channel state as empty on the channel on which the marker has come. Now here the underlying assumption is the channel is a FIFO channel. FIFO channel means first in first out. So a message, two messages sent one after the other from on a channel will be delivered in the same order. That's what a FIFO channel means. So if a process is sending a marker, if it is sending a message after sending the marker, then the receiving process should first receive the marker and then only should receive the message. So if whoever records the local state of a process and sends the marker, then the receiving process should receive the marker. And if any message has been sent after sending the marker at the sending process, the receiver should get that message only after receiving the marker. So this kind of satisfies the requirement of guaranteeing a global state, a consistent global state. Now, when a receiving process receives a marker, it has also already recorded the global state, that is else part, or this actually this part. If the process has already recorded the global state, then when it receives every message that has been received after it recorded the local state should be recorded as being in transit, basically on the channel. Okay, so that's the status of the incoming channels. So when a process records the local state because of receiving a marker, it records, that's the else part here, it records basically all the messages that have been received so far and sent so far in its local state, and it records the state of the channel as being empty on the channel on which the marker came, because every message should have been received before the marker has come, if at all they were sent. And it records the state of the channel as empty and then sends out the marker on all the channels to which this process is connected. Okay, so the marker is sent out again only if the process records its local state at this time when it receives a marker. If it has already recorded this local state and it receives a marker, it doesn't send out a marker again on the outgoing channels. So after a process records its local state and the states of all its incoming channels, then it sends out the local state and state of all the incoming channels to the initiating process that puts together all the global states, all the local states and channel states, and arrives at the global state. So let's look at an example of the execution of this Chandy-Lamport's algorithm. So these are the sequence of messages that are being sent and received across a distributed system, and all messages satisfy the causal ordering property. So this message is sent from process P3, so it's incremented one time clock, and then it is received at process P4, so I have incremented this clock value at 1, and all these other entries come from this process. And then this guy P2 sends, so this is incremented by 1, and then to P1, so this is incremented to 1. Then P1 sends is incremented to 2, to P3, so P3 has 1 event so far, it increments another 1, so it's 2 now, and all the other entries came from this P1. And then P4 sends to P2, so this is incremented from 1 to 2. For P4 is a sending event, and then at P2 it is incremented from 1 to 2, and the component-wise maximum gets you 0, 2, 1, 2. And then P2 sends a message to P1, so P2 increments this entry from 2 to 3, and P1 increments this as 3, and then the component wise maximum, so maximum of 1 and 3 is 3, maximum of 0 and 1 is 1, maximum of 0 and 2 is 2. And then P3 sends a message to P1, so it's incremented from 2 to 3, and P1 increments from 3 to 4, and the rest is component wise maximum, so this is going to be maximum of 1 and 3 is 3, maximum of 3 and 1 is 3, maximum of 0 and 2 is 2. Then P3 sends to P4, so it's incremented from 3 to 4, and then this is incremented from 2 to 3, maximum of this and this is 2, and 0 is 2, maximum of 1 and 0 is 1, 4 and 4, 1 is 4, and 0 and 2, 3 is incremented, so 3. Then P2 is sending a message to P4, so this is incremented from 3 to 4, and this is incremented from 3 to 4 here, and the rest is a component wise maximum. Maximum of 0 and 2 is 2, 4 and 1 is 4, 1 and 4 is 4, and then this is incremented from 3 to 4. Okay, so now we want to record the global state. So these are the messages that have been sent and received, and these are the clock values. So the initiating process is our process P1, so it initiates at this time instant. So so this is of course the process graph. So we have P1 being able to send to P2 and P3. Okay, so so P1 records the current timestamp, which is 2100, and so at this time it has not received anything else, so it sets out the marker on its two outgoing channels, which is to P2 and P3. So the state of the channels are not yet known. It just when you start the recording, so you basically record your local state and send out the marker on the outgoing channels. Okay, so the before that, so this is the local state P1 2100, and the marker now goes to P2 and P3. So P2 and P3 have not yet recorded their local state, so they will record their local state, and as well as record the state of the incoming channel as empty. So now let's look at how 2 records its local state. So for 2, 0312 is the time before at this point. So it records its local state to be of timestamp 0312, and the state of the incoming channel from 1 to 2 is recorded as empty because the marker is received now. So now 2 sends out the marker on its outgoing channels, which is back to 1 as well as to 4. It sends out the marker. Now when 1 receives this message, it has already recorded its local state, so it simply records the messages that have been received after it recorded the local state as being the status of the channel. So it records this message, the timestamp C21 as the status of the channel from 2 to 1. And now P3 records its local state when it receives the marker for the first time, and its timestamp so far is 2140, and it records the state of the incoming channel from 1 to 3 as empty. So when you record the local state, you record the state of the channel as empty because the marker came, its marker is the last one to come, and you send out the marker on all your outgoing channels. So P3 now sends it out to P1 and P4. So now P1 records the state of the channel because it has, when it receives the marker from P3, it has already recorded its local state. So all it has to do is record the state of the channel from 3 to 1. So whatever the message was received after the recording of the local state is the message on the channel. So this 3143 3.2, this message is now recorded as the state of the message of the channel from 3 to 1. And now it's the turn of P4. It receives the markers sent by P2 and P3, but it receives the markers sent by P3 first. So it records the state of the channel, state of the process at that time. So at that time its state is 2143. That's what is the state of the process at P4, and it receives its marker from 3 to 4. So the state of the channel from 3 to 4 is recorded as empty, and it sends out on its two outgoing channels to P3 and P2, which is shown here. Now P3 and P2 have already recorded the local state, and they have not received any process from P4 after they recorded the local state. So the state of the channel from from 4 to 2 as well as from 4 to 3 would be empty. And so essentially now these were the time instance or the cut events where it recorded the local state, this time, this one, this and this. So if I can put together all those cut events, so I get what is called the global state or the global cut. So the time across this cut events is essentially this 2100 across all these processes. And so the maximum of this is 2, that came from P1. The maximum of this is 3, that came from P2. The maximum of this is 4, that comes from P3. And the maximum of this is 3, that comes from P4. So it's a consistent cut, but it is not a strongly consistent cut because we have two messages in transit. You see the channels, the state of the channels is not empty. We have two messages in transit, one on channel from 2 to 1 and one on channel from 3 to 1. So if all the channel states are empty and the cut satisfies the property that the individual values should have come from the corresponding process, then the cut is a strongly consistent cut. So in this case it's just a consistent cut. So let me just add this comma here, and I can even put this thing to make it look consistent. Okay. All right. So the complexity of this is essentially going to be the number of messages that were sent, and in terms of message complexity, and time complexity is how long it takes for the processes to collect the local states. So the messages is essentially the messages are sent across all the edges in the process graph. So if E is the number of edges in the process graph, you send that in both directions. So it is 2E. So it's still, we can say, theta of E. In terms of delay, it is theta of D, where D is the diameter of this process graph. Diameter is essentially the largest value for the minimum number of hops between any two vertices on a graph. So 2 is the diameter of this graph because any two processes are connected no more than 2 hops, right, on the shortest path. So it takes essentially 2 time units for the processes to have collected this local states, and then of course you have to send everything to the initiating process. Now in terms of the correctness of this, which we already discussed, the first condition is if the sending of a message is recorded in the local state of the sending process, then the receiving of the message should have been either recorded in the receiving state of the state of the receiving process or as being in transit on the communication channel. And now due to the FIFO property of the communication channels, so if a process receives a marker and it has not recorded the local state of itself, then it records all the messages it has received so far. So if the marker is received at that time, then the sending process should have sent the message before sending the marker, and the receiving process has received the message because it's a FIFO channel. So if some message is sent before the marker is sent, then that message should have been received before the marker is received, right? So if a message is sent and then the marker is sent, that the message should be received and then only the marker should be received, because the communication channel is FIFO. So that guarantees that if you have not recorded the local state and you receive the marker, you are recording the receiving of the message in your local state. Now, if you receive the marker and you have already recorded the local state, then what happens? You're recording the message as being on the state on the communication channel. So either way, you're capturing the sending of the message. Right? So if the sending of the message happened before the sending of the marker, and when the time the marker comes, if you've already recorded the local state, then you're recording the message as being in transit. So the sending of the message is now captured in the channel state. Whereas if the sending of the marker of the message happened before the sending of the marker, and when you receive the marker, you have not yet recorded the local state, you're receiving because of the FIFO property of the channel. The message should have been received before you receive the marker. So when you receive the marker and you are recording the local state, you will be recording the receipt of the message also as part of your local state. Now, if the message is the sending of the message is not recorded in your local state of the sending process, which means the message was sent after the marker was sent, then the receiving process is not going to get that message before the marker is received. So, which means when a process records its local state at the time of receiving the marker, it records only those messages that have been received until then. So, since again the communication channel is FIFO, you are not going to record the receiving of a message before you receive the marker. Right, so the message is going to come to you after only the marker has come, because the sending of the message happened after the marker was sent. So you are also going to get the message only after the marker is received. So you're not going to consider all those messages that were received after the marker was received. So that guarantees that you are not going to record either in the local state as well as in the communication channel, because in the communication channel also, if you receive the marker, you are going to record all those messages that were received after record the local state, but before the marker was received, because again the channel is FIFO. So you're not going to look at things beyond what happened after the marker was received. Okay. So that's exactly like this message that was received after the marker was received. So I'm not going to worry about that message at all. Okay. Notice that this is a FIFO channel, so this marker is sent here and the message was sent here. So if the channel is not FIFO, then it would have been possible the marker sent from here could have come after the message was delivered. But since the channel is FIFO, the marker is sent first and the message is sent after that. So the message is going to come to this process only after the marker is being received. So there's no way I will capture the receiving of this message unless the message was sent before the marker was sent. So if the message was sent before the marker was sent and I received like this, then essentially the marker should have been received after the message is received. So in that case, that message would be captured as a transit message. But we don't have all these things in this example, but I'm just telling with regards to this message, again, the underlying communication channel is assumed to be FIFO. If the channel is not FIFO, then this algorithm basically fails. So for this algorithm to work, you need the communication channel to be FIFO, like we see here. This process P2 sends to P4 first the marker and then the message. So first the marker should come to P4 and then only the message should come to P4. Okay, so I'll stop here.